So good morning, I am Krishna Kumar. We continue the discussion on the Jordan form from where we left it last time. Let us recall some of the facts to fix these ideas. Now this is the gist of what we did last time. So we have a linear transformation V, and we have assumed that the characteristic polynomial, so the characteristic polynomial f lambda is of the form where lambda I is different from lambda j whenever I is different from j. Now di is the multiplicity of lambda I. Yeah. So the characteristic polynomial, we are assuming the characteristic polynomial split into linear factors, the product of linear factors. Now this happens if we assume the field F is algebraically reduced. Even otherwise it can happen. So a sufficient condition for this scenario to emerge is that the associated field is an algebraically closed field. There are examples where even otherwise this splitting into linear factors may happen. But what we need is that it splits into linear factors. Now then what we have is that the minimal polynomial where of course we had this one d1 plus n di is greater than or equal to 1 for every I. Now this is the assumption that we have. Now here what we have is that 1 less than or equal to Ri less than or equal to di for I you know that the minimal polynomial divides the characteristic polynomial, and every factor of they have the same zeros. This is another property. Therefore, again the factors here are lambda minus lambda I for I running from 1 to k. Okay. Then what we have seen is that if we define Wi, this is the primary decomposition theorem, is the null space of t minus lambda I to the power Ri. Okay. Wi is invariant under T. And V has a breakup of now you see this breakup is unique up to the order in which we choose this lambda 1, lambda 2, etc., lambda k. Once we fix the order, this breakup, the choice of Wi's are unique, and the breakup that you have is also unique. So we fix a certain order in which it is taken. Okay. Now what you have is that, we define Ti belonging to L Wi as that is restricting T to Wi. So it defines another, induces a linear transformation on Wi, and this induced linear transformation is denoted by Ti. Then you also have the minimal polynomial for Ti is to the power Ri. Incidentally, dimension of Di, that is the multiplicities of lambda in the characteristic polynomial. Okay, so we denote this by, so let this one. Now this is the content of primary decomposition. In fact, we have proved it for more general cases. Okay, so it's a special case where you have the restriction on the characteristic polynomial. Right, now what we do is we try to break up this operator again. Right, now we want to bring in the cyclic decomposition also into the picture without any major change in this breakup. So within this breakup we want to bring in the cyclic decomposition. So what one does is this. Okay, now consider Ti. On Wi, we have direct dimension of Wi equal to Di. Okay, therefore what do we do? So we define Di I on W, identity operator. It's a diagonal operator. In fact, a diagonal. And if you choose a basis for, if we choose any basis for Wi, then T, the representation of T with respect to Ti B I equal to where Bi is any ordered basis for what Di? This is Di. For Wi. This is what we have. Now define so Ni belongs to Wi. Then what you have is this. Di is this. What we have is that then Ni is nil product. With characteristic polynomial lambda to the power Di and minimal polynomial Ri. This Ri, the same Ri that is appearing here, okay, this is what we have, right? Therefore, what we can do is now consider the cyclic decomposition of Ni. What do we have? We have a breakup of Wi is broken up into this is in fact true for every Ni. I mean every I this is true. Okay, so this is what you get. This is true for every I. And what we have is that this breakup that you have, that means cyclic. So we have, what we have is that there exists vectors Vi1 which generates the corresponding cyclic spaces. Which generates the corresponding cyclic spaces Zi1, Zy2, etc. Zin. Okay, and we also have information about the dimensions of Zi1, Zi2, etc., Zin. So we have from the cyclic decomposition theorem, from the knowledge of what is called the minimal polynomial for Ni, we have the following information. So we have what you call the dimension of Zij Vij Ni is given by Rij, and with the property that Ri is equal to Ri1 is greater than or equal to Ri2 Ri. This is what you have. And you also have that Ri1 di. This informations we have. Okay. So what you have is that suppose I denote by Bij this is the basis generated by Wij. Okay, now put them together. Okay, so if you put together the following one, that is, we can denote by B tilde I it's an ordered basis for W I. Now if we go for the representation of, so then so we can write it down now using the cyclic decomposition theorem. It's very interesting. See this. this is equal to, see, you recall the our this condition, Ri equal to Ri1 greater than or equal to Ri2, etc. Therefore, we have got the cyclic decomposition given by the following. Okay, let me write this. It's a di cross di matrix. It's a di cross di matrix. How does it come? It comes like this. Blocks so the first block is an Ri1 cross. So this is an Ri1. It's an Ri1 cross Ri1. And this is Ri2 Ri2. And this is of course Rini cross I. So this is how it comes. And how does it look like? It looks like along the diagonal you get 0. The diagonal below the main diagonal is filled with 1 and so on. It is 0 here. Or each one of this is of the following type. I'll magnify it and put it here for your reference. Each one, this is an Ri cross Ri. With along the diagonal you have 0, then you have this is what I write there. You have got 1 here, 0 here, 0 here, 0 here. Then you have 0, 0, 1. One here, this is what you have. This is the shape of this matrix. This is Rij cross Rij for various values of j. Okay, j running from 1 to n. Okay, so this is the typical form of the matrix. Each one of them is like this. Now you see that this is R1, Ri1, this is Ri2 dimension, this is Rini dimension. So the sum of all these will together will make it Di. Okay. Now we observe that Vij for j belonging to Ni and are eigenvectors of di belonging to the eigenvalue lambda I. Now this is true for every I that is corresponding to each one of these wi's that you have. So we make this observation. Therefore, what you observe is that because bij's are from W, in fact every vector in Wi is an eigenvector of di. In fact, every vector lambda I. This is true for therefore the structure of or the representation for di with respect to any basis that you choose for Wi will remain the same. It is diagonal, with all diagonal entries being lambda I. Using this fact, so it doesn't matter what basis you choose for Ni. So what we are going to do is, we are going to choose a basis for Ni. When you, a basis for Wi, as we have starting from working with bij's and putting them together, etc. They are all in Wi. What is the consequence of that? Then what you have is this. So we will, the representation for Ti, representation for Di plus representation for Ni with the same basis. Okay. Right? So this is true. So what is that you obtain then? Then we have the following matrix representation. So we have already computed the matrix representation for Di. We have already the matrix representation for Ni. Put them together, add them together without any inhibition, because that does not depend on the particular choice of the basis for Wi when it comes to computation of Di. It only matters for Ni, and that we are going to fix. So we are going to fix the basis dictated by the cyclic decomposition of Ni. So with respect to that basis, this is what you get. Then you have takes the following. What happens is that, look at this representation, the diagonal elements will be coming in, they are lambda I, etc. lambda I. So this is what you have. So you have again the first block, this is an R1, R, cross R1, which is the same as Ri1 cross, what is that? This is Ri cross Ri, no? Yeah. This is R and then you have got eventually this is the matrix. And what are the entries that you have? The entries are lambda I, I along the diagonal. And you have this is again lambda I, only difference is in the size of the matrix. Here also lambda I, all the diagonal entries are lambda I. Okay, so that is pretty clear how it comes up. Okay? So this is a representation for VAT. Now what we do? We want to get the matrix representation for this one. So let me call that AI denote then put these ordered bases together to get a ordered basis for V. Okay. Vk tilde in this particular order, then what one gets is this. Okay. Then what do we get? We get the matrix representation for T would be emergent. Then what one gets is the following. The into blocks A1, AK, 0 along the diagonal. The blocks A1, A2, etc. AK along the diagonal where AIs are defined in this way. So each AI looks like this, the corresponding alpha. Okay. So AI is the, what is that, DI cos now this is the okay. So I think now it must be pretty clear what kind of this is, and we will look at some examples towards the to find out exactly how they look like in some where you will not get confused with the indices that are various indices that are coming. Okay. Now what remains is to assert that this representation is unique. So uniqueness in what sense? So this is called, A is called a Jordan matrix. So let us define that first and then go like this. Any matrix in this format is what you call a Jordan matrix. So a matrix satisfying all the conditions satisfied by A called a is said to be in Jordan. So this is the definition that we have. Now what we want to prove is that this Jordan form that you choose for a given T is unique up to certain factors. So what we have proved so far is that there exists a Jordan form representation for the given linear transformation, provided the characteristic polynomial breaks up into the product of linear factors. That's the only condition that is. Okay. Now suppose, let us assume that there exists an ordered basis for V in which T is represented by a Jordan matrix. then each AI is a DI cross where DI is the multiplicity, the algebraic multiplicity of lambda I as a characteristic polynomial A and that of hence that of T, because both T and A, as long as A represents T, they have the same characteristic polynomial and the same features. That is called. And hence that of T. Or and once we fix the order of lambda 1, lambda 2, etc., lambda k, the lambda i's and the di's unique once we fix at the order in which the zeros are written. So once we fix the choice, then everything is done. Okay. Now A is the direct sum of matrices AI of this DI cross A. This gives a direct decomposition B as WK, where WI equal to the null space of T minus lambda I to the power Ri comes from the index of the multiplicity of lambda minus lambda I for the what is called the minimal polynomial of Ti. Okay, right. See, note that A minus is regular okay is singular whereas on Wi singular and A minus lambda Ji is regular, is non-singular, for J not equal to therefore what do you have? See, these Wi's are uniquely fixed. Therefore, Wi's are uniquely because once you fix the order for lambda I, then it is true. So now we take Ti. So Ti is the operator induced by T on Wi. Then Ai is uniquely determined as the rational form for Ti. And this comes from Ni that we have seen. So this is about the uniqueness. So you have here, first of all, there is the breakup for for V induced by what are called the zeros of the characteristic polynomial of T. The second part is what is called the define these so-called NIs, and these NIs are nilpotent operators, and then they have got their rational form determined uniquely, and you know the rational forms are determined uniquely, and then of course you see, you put them together, you get this. So once, the only point is that once you choose the choice of lambda i's, in which order you choose is once you fix that, everything is uniquely determined. Okay. Now we look at some problems related to this, which will throw some light or insight into this. First question is what are the Jordan forms of T belonging to okay. What do we have? You know that you take f lambda. F lambda is splits into linear factors. It is actually lambda minus lambda 1 into lambda. Now there are two possibilities here. The first possibility is that first example, lambda 1 minus lambda 1 not equal to lambda 2. Okay. In this case, what is the minimal polynomial? Then lambda. So in that case, what happens? The operator T is diagonalizable, and then the Jordan form see, what you have is that there is the W1 and W2 are dimension. That's the reason. B. The second possibility is that lambda 1 equal to lambda. In this case, what happens? See, f lambda is square. So in that case, there are two possibilities for p lambda. So p lambda may be lambda minus lambda 1 or square. So there are two possibilities. So first we take the case then what you have, then what we have is that this is again diagonalizable, and you have, you see, this is the space would become, you see that if you go for the cyclic decomposition, this is what you get, lambda 1, 0, 0 is the Jordan. So here the V is equal to W, but what happens is that you take the decomposition. If you take the decomposition, you have the first block given by the degree of P, and that's equal to 1. So you get a 1 by 1 block and another 1 by 1 block, and they are going to be lambda 1 and lambda 1. Now let us take the next possibility. The next possibility is that the second possibility is that P lambda equal to then in the Jordan form you have only one block. And therefore that is given by lambda 1, 1. So these are the possible representations of a 2 by 2 of a operator on LC. The second example. Now we take A okay, there are three parameters there, A, B and C. And of course this is in A, C3, right? Then you see that is easily computed. F lambda in this case computes as lambda minus 2 whole square into lambda plus 1. Then there are two possibilities. The possibilities are the following. There are two possibilities for the minimal polynomial. What are the possibilities? One is that lambda minus 2 whole square into lambda plus 1 itself. The other one is lambda minus 2 into lambda plus 1. So there are two possibilities. First possibility is P lambda equal to lambda minus 2 whole square. In this case, what you have W1 and W2. This is two-dimensional corresponding to the eigenvalue, and this is one-dimensional. This is what you have. Okay, lambda 2 equal to minus 1. Right? That's the breakup that you have. Then what happens? In this case, you see that in W1, dimension of equal to the cyclic decomposition or the Jordan form T1 0 1 and T2 therefore the Jordan form for T2 equal to minus 1. Therefore, the Jordan form this is the Jordan form. And what happens in the next possible case? Oh, okay. Okay, right. Here, of course, what you see is that dimension of now what you have. So the case 2, let us write it up. This is case 2. Case 2 is where the P lambda then T1 is, again there is a breakup for that. Minus 2. And W1 is 2-dimensional. Therefore, it breaks up into a 1-dimensional, a 1 by 1 matrix plus another 1 by 1 matrix. Therefore, what you have? You have T1 into this one. This is a 1 by 1 matrix, this is a 1 by 1 matrix. That's how it breaks up. And T2, of course, is a 1 by 1 matrix, and this is hence the Jordan form for T is given by 2, 2. Now let us make a computation on what this P lambda turns out to be. As we compute if we compute PT for then Let's, if you compute, this will turn out to be simply this. Now you see that f lambda, that is p lambda equal to is the minimal polynomial only if you see these two become 0. And this is if and only if therefore the condition is that so C can take any value, but A, if A is 0, so there are two cases. One corresponds to A equal to 0. So this is the situation where A is equal to 0. The other situation is that where A is not equal to 0. Okay, so that's about that example. Now we take a third example. Look at the D operator. Now you know that this is defined by, so D is defined by D of 1, 0, D of x, D square, D of equal to, therefore if we choose B equal to 1x, x square, x cube as the ordered basis, C, then the matrix for D with respect to B is given by the following. Zero. This we know. This is very simple. Now we look at the Jordan form for this. Jordan form of D on So what about the characteristic polynomial? The characteristic polynomial of D is f lambda equal to lambda to the power 4. And what is the minimal polynomial? The minimal polynomial that you have is the following. Also, why? Because if you take dq of, say, operating over x cube, okay, dq operating over x cube is equal to d square of 3x square, which is equal to d of 6x, which is equal to d, which is equal to 6 and not equal to 0. Because d to the power 4 of any polynomial px this we have. Okay, therefore this is the minimal polynomial is also equal to, hence therefore for the 4 by 4 matrix, what is the corresponding minimal polynomial? Because all the eigenvalues are 0, and then you have got off diagonal this is the line. So this is the joint. Okay. So I think let me stop this with this example. Maybe I will give one more lecture on this topic. Continue with consideration of some more examples, which will throw some more light into the working of this. Okay, so thank you very much.